2.3 Lesson 2, the limit theorems. Our objective for today is this. You will be able to use the limit theorems on page 42 to find limits of functions. And vocabulary, we saw this yesterday. These are the different limit theorems that we have. And we'll be using them to do problems that we're looking at today as well. The limit of a constant function. You can look at lesson 1 to look at these particular results that we considered yesterday. The limit of the identity function, the limit of a constant times a function, the limit of a sum of two functions, the limit of a product of two functions, and the limit of a quotient of two functions. And as we discussed yesterday, all of these are derived or proved using the epsilon delta definition of limit. But once we've done that, we don't need to use the epsilon delta definition of limit directly. Instead, we can just use these theorems. And that would be proving the limits that we're finding. Ultimately, it goes back to the epsilon delta definition of limit. However, we're using the epsilon delta definition of limit indirectly, because these are all based on the epsilon delta definition of limit. We will take a look at two examples for today's lesson. Here's our first example. The function is f of x, as you see here written in black ink. Let's look at the instructions for this problem. Plot the graph using a friendly window with the given value of x as a grid point. So we want to find the limit of this function as x approaches -1. So the given value of x would be -1 because x is approaching -1. Sketch the result, sketch the graph. Show that the function takes the indeterminate form. So let's look at the graph first. So here we're looking at the graph of our function f of x, which has been entered into Desmos. And the graph is a parabola. However, there is one point that is missing from the parabola, and that happens at x is equal to -1. And the reason why we have a gap in the graph at x is equal to -1 is because the function f, if you were to try to evaluate that at -1, the denominator would be 0, and the numerator, you can evaluate the numerator, but whatever the numerator might be, you cannot divide by 0. So the function is not defined at x is equal to -1, and the graph would actually have an open circle at x is equal to -1, or a gap in the graph. The numerator would also be 0 if you were to evaluate the numerator at x is equal to -1. So you get this indeterminate form, 0 over 0. And that's what the instructions are stating for us to do. It says, plot the graph using a friendly window with the given value of x as a grid point. The given value of x is -1 because that's where we're taking the limit. And this is the graph that you get with a gap at x is equal to -1. Sketch the result. You see the graph here. Show that the function takes the indeterminate form 0 over 0 as x approaches the given value. There it is. Simplify the given fraction. Find the limit. So we want to simplify the given fraction. We want to find the limit and prove that your answer is correct by naming the limit theorems used at each step. So that's like what we did yesterday. So how do we simplify this function? We will see if we can factor the numerator, and perhaps one of the factors will be x plus 1, and if that's the case, we can cancel the common factor of x plus 1 that's in the numerator and the denominator, and that would take care of simplifying the function. And then we can find the limit, as we did yesterday, by using the limit theorems, and prove your answer is correct. As long as you're using the limit theorems, you know your answer will be correct. So you just cite the limit theorems that you're using at each step. So let's take a look at how we can factor the numerator of the function and then cancel the common factor of x plus 1 that we will find in the numerator, which of course is also in the denominator. By the way, before I even do that, just from the graph that you see here, we know there is a gap at x is equal to -1, but we expect this limit to be equal to, as x is approaching -1 from the left or from the right, we can see from the graph that the y values are approaching -3. So the answer that we're expecting is -3, but when we use the limit theorems that we learned about yesterday to do it, as you're about to see now, that would be proving that the limit is -3, because again, the limit theorems are ultimately derived from the epsilon delta definition of limit, so you can be confident that the limit is, in fact, whatever you find it to be, which will be -3 for this problem. So we like to begin this simplification process by factoring the numerator, and let's see how we can factor x cubed plus x squared minus 4x minus 4. So we have a polynomial expression with 4 terms, so we will try to factor the numerator by grouping. So we group the first 2 terms, and we group the last 2 terms. So I haven't really changed anything. I've just put parentheses around the first 2 terms and parentheses around the last 2 terms, and there is a plus sign between them. So there's really nothing that I've done except grouping terms. So now from the first group, there is a common factor of x squared that I can factor out from each term. When I factor out x squared from the first term, I'll be left with x from x cubed. And then when I factor out x squared from the second term, I'd be left with 1. And you can see that I've done this correctly. If you multiply the x squared back to x plus 1, you'll get x cubed plus x squared. So it's just a different way of writing x cubed plus x squared. Now, you would like to factor something out from the second group so that you would also be left with x plus 1. So if I were to factor out -4, then from the first term I'd be left with x, and from the second term I'd be left with plus 1. So the reason why I factored out -4 is because I am left with x plus 1 after I factor out -4. Because now we have this plus sign, and we have these 2 terms that are added, and the 2 terms have a common factor of x plus 1. So we can factor out x plus 1 from each term. From the first term, I'd be left with x squared, and from the second term, I'd be left with -4. You may remember a factoring pattern called a difference of 2 squares. So here I have x squared minus 4, which is 2 squared. Whenever you have a squared minus b squared, you can factor that as a plus b times a minus b. So we can go ahead and factor that as x plus 2 times x minus 2. And I have factored the numerator. So I'm able to rewrite my function f as you see on my screen now. I'll go ahead and erase the factoring work. The next step is I can see that there is a common factor of x plus 1 that I have in the numerator and the denominator, and I can cancel that. So I'm able to simplify my function as x plus 2 times x minus 2. I do have to write that x cannot be equal to -1 to remember that in my original definition of f, I had the x plus 1 factor in the denominator, which would exclude -1 from the domain. So now I'm ready to go ahead and find the limit of f of x as x approaches -1. And the reason why I can use the simplified version of f of x to find the limit of the original function as x approaches -1 is, remember, if you go back to the definition of limit, you will see this part of the definition, but x is not equal to c. And the reason why we have that in the definition of limit is, as we understood when we were looking at limits numerically and graphically to understand limits conceptually, we understood that conceptually this is what a limit means. As the input values for f get closer and closer to 1, the output values get closer and closer to what number? So it doesn't matter if the function is actually defined at c. In this case, c would be -1. So because it doesn't matter if the function is defined at x is equal to -1, we don't need to use the original function. We can use the simplified function with the note that x is not equal to -1. Because again, for the limit, we don't care what's happening at x is equal to -1. It's okay if the function is not defined there. We want to know what's happening as the input values for f get closer and closer to -1, what's happening to the output values. So that's basically what we need to do, so we can use the simplified version of f to do that. So we begin our problem by writing f of x as x plus 2 times x minus 2, and we want to take the limit of that as x is approaching -1. We can recognize that what we have here is a product, and we can use the limit of a product of two functions theorem. So we have the limit of a product, and that's what I'm using to rewrite my limit as you see here. And what I've done here is I've looked at this and I see that I have a sum of two functions. So one is the identity function and the other is the constant function. So if I have a sum of two functions, I can write that as the sum of two limits. So this is called the limit of a sum of two functions. And here I'm seeing this as a sum of x plus -2. So I'm also writing this as the limit of a sum of two functions. And what you can see here is that you have the identity function. So you can write this as the limit of the identity function as x approaches -1 is -1. And the property for that would be limit of the identity function and then here you have a constant function, and we know that the limit of a constant function as x approaches c would be just the value of that constant, so it would be 2. So your justification would be limit of a constant function, and then you have times this product, because originally we began with using the limit of a product, so you have that product there. And then here again, what is this? This is the limit of the identity function. So the limit of x as x approaches -1 would be -1, and then plus the limit of a constant function once again. The limit of the constant function f of x is equal to -2 as x approaches -1 would be just -2. So again, we're using the limit of the identity function and the limit of a constant function once again. So when you do that, you have -1 plus 2 is 1, and then you have 1 times -1 plus -2 is -3. So you have 1 times -3, which is, of course, -3. And that's the limit that we were expecting when we were looking at the graph. As you can see from the graph, we were expecting the limit of f of x as x approaches -1 to be -3. But what did we do? We simplified the given fraction, we found the limit, and we proved that our answer is correct by naming the limit theorems used at each step. We're going to take a look at a second example now. So now we take a look at a second example, and the same instructions, plot the graph using a friendly window with the given value of x as a grid point, and since we're taking the limit of the function f of x is equal to x squared minus x minus 6 divided by x plus 2 as x is approaching negative 2, we want to include x is equal to negative 2 in our window settings. So plot the graph using a friendly window with the given x value as a grid point, sketch the result. The graph is a line, but there is a gap in the line, or a hole in the line, at x is equal to negative 2. And the reason why we have that is because the function f is not defined at x is equal to negative 2, as that would result in division by 0. Sketch the result. So the result is a line with a discontinuity at x is equal to negative 2. And later, when we learn about continuity, this is called a removable discontinuity. So sketch the result. There it is. Show that the function takes the indeterminate form 0 over 0 as x approaches the given value. So when we substitute negative 2 for x in the function, in the denominator we'll get 0. In the numerator, negative 2 squared is 4. Minus negative 2 would be plus 2, and then we have minus 6. So we have 4 plus 2 is 6. 6 minus 6 is 0. So we have that indeterminate form 0 over 0. So show that the function takes the indeterminate form 0 over 0 as x approaches the given value. So what that means is that negative 2 is a 0 of both the numerator and the denominator, which means the numerator and the denominator will have a common factor that we can cancel out. And how do we know this? Because the function f evaluated at negative 2 gives us 0 over 0. If the numerator had not been 0, then what you would have is some kind of a vertical, you would have a vertical asymptote for the graph at x is equal to negative 2, rather than a gap in the graph at x is equal to negative 2. For this problem, we have a gap and we have a removable discontinuity, as you will learn in the next section. But if the numerator had been different, but the denominator the same, then if the numerator is not equal to 0 at x is equal to negative 2, but the denominator is equal to 0, then the graph would have a vertical asymptote at x is equal to negative 2 and a non-removable discontinuity. But that's for later. So like in the first example, now we want to simplify the given function, find the limit, and prove that your answer is correct by naming the limit theorems used at each step. So we will simplify the function by factoring the numerator and canceling a common factor in the numerator with x plus 2 in the denominator. And then we will find the limit by using the limit theorems. And right before we do that, we do want to take a look at what we are expecting to be the limit. From the graph, you can see that as the input values approach negative 2 from either direction, the output values of the function are approaching, it looks like, negative 5. So we're expecting this limit to be negative 5, and when we use the limit theorems, after we simplify the given function, we will be able to find the limit to be negative 5 by using the limit theorems. And that would prove our answer to be correct, because the limit theorems are based on the epsilon delta definition of limit. Thus, our answer would be justified analytically. So we'd like to simplify this function by factoring the numerator and then canceling the common factor of x plus 2 that we will have in the numerator as well as the denominator. So how do we factor x squared minus x minus 6? This is a quadratic trinomial. We say it's quadratic because it's second degree, and trinomial because we have three terms. This is a quadratic trinomial. How can you factor a quadratic trinomial? You can either guess and check, which is pretty easy to do in this problem, or you can do something called the British method for factoring quadratic trinomials. So if you want to use the British method, here's what you must do. You're going to multiply the quadratic term by the constant term. X squared times negative 6 gives you negative 6x squared. And then you need to find two terms that will multiply to give you negative 6x squared, but that will add to give you negative x. So if you multiply negative 3x by positive 2x, you will get negative 6x squared. But when you add negative 3x to positive 2x, you get negative 1x. So these are the steps that you have to follow to use the British method for factoring a quadratic trinomial. Again, you begin by multiplying the quadratic term by the constant term, and then you find two factors of negative 6x squared that will add to give you the linear term from our original quadratic trinomial. And once you have that, you're just going to write the quadratic and the constant terms. So you have x squared minus 3x plus 2x minus 6. So in other words, this is exactly the same as what we started with, but it's just written differently so that we can factor this by grouping. We can factor this by grouping, and just like we did in example 1, because now we see four terms here. So from the first group we can factor out an x, and then I will have x minus 3. And I'd like to factor out a 2 from the second group so that I would also be left with x minus 3. So now I have this plus sign, I have these two terms, and I can see that they have a common factor of x minus 3. So I will factor out x minus 3 from each term. From the first term I'm left with x, and from the second term I'm left with positive 2. So that's how you factor the numerator. You could have also just guessed and checked. If you guessed that this is how you would factor the quadratic trinomial, you can do FOIL here to see that it is in fact the same as x squared minus x minus 6. So now we'll go ahead and write f of x is equal to x squared minus x minus 6 factors as x plus 2 times x minus 3, and the denominator is of course x plus 2. So having done the factoring, I'm going to go ahead and erase the work for factoring. Again, I got x plus 2 times x minus 3 as I wrote here. Now we see a common factor of x plus 2. That's in the numerator and the denominator, so we can cancel the common factor of x plus 2 and simplify our function to be just x minus 3, with the note that x cannot be equal to negative 2. So now we're able to take the limit of f of x as x approaches negative 2, and this is our function f of x, but we may replace it with the simplified version of f of x for the purpose of taking the limit as x approaches negative 2. And the reason why we can do that substitution for the function f with the simplified version is because when we take the limit of f as x approaches negative 2, our conceptual understanding of what a limit is began by thinking about it as you see here. As the input values for the function f get closer and closer to, in our particular case here, negative 2, the output values get closer and closer to what number? So we don't really care what's going on when x is exactly equal to negative 2. And as we've seen with our conceptual examples that we looked at graphically as well as numerically, in fact, the function can be undefined at x is equal to -2, and the limit could still exist. And that's what's going on here. So basically, you can replace the function, the original function f, with this simplified version, because these two functions are exactly the same except at x is equal to -2. The original function's graph would have a gap at x is equal to -2.
You're muted at your...
So let's get back to what I was saying. So these two functions, they are identical except at x is equal to -2. Our original function is not defined at x is equal to -2, whereas if you just look at f of x is equal to x minus 3, of course, to make it to note that it is our original function, we have to give this restriction that x cannot be equal to -2. But of course, if you just had f of x is equal to x minus 3, the only difference between f of x is equal to x minus 3 and our original function is not defined at -2, but this function f of x is defined at -2. And as far as finding the limit, it doesn't matter that this function is not defined at -2. So we can go ahead and use f of x is equal to x minus 3 and find the limit of x minus 3 as x approaches -2 using the limit theorems, and it would give us the same limit as that of the original function. Again, it doesn't matter that the original function is not defined at -2. And you can also see that in the definition of limit, there is that exception that x is not equal to c. You can also understand what we just stated graphically. What difference does it make if this gap were there or if it were not there, as far as finding the limit of the function as x approaches -2? Either the function could be undefined at -2, as f is undefined at -2, or you can fill that gap in, but it would not make a difference for the limit. The limit would still be -5. So to summarize, we can replace f of x with x minus 3 because these two functions agree for all values of x except x is equal to -2, but when we're finding the limit as x approaches -2, it doesn't matter what's going on at x is equal to -2. So we can simplify our work by replacing f of x with x minus 3. So now we're ready to complete the problem by using the limit theorems that we learned about yesterday. You have x minus 3, which you can write as x plus -3. And then here you have a sum of two functions, so you can write this as a sum of two limits. The limit of the identity function as x approaches -2 plus the limit of the constant function -3 as x approaches -2. And the property that I used here is the limit of a sum of two functions. So what is the limit of the identity function as x approaches -2? It is -2 plus the limit of the constant function -3 as x approaches -2 is -3. So what properties or what theorems did I use here? So I used the limit of the identity function theorem and the limit of a constant function. And when I add -2 and -3, I get -5. That is my limit, and it is proved using the limit theorems. And since these are based on the epsilon delta definition of limit, ultimately I have proved this limit to be correct using the epsilon delta definition of limit. And of course, this is what we were expecting when we looked at the limit graphically. So today we looked at being able to use the limit theorems to find limits of functions. These are the limit theorems. They were derived or proved using the definition of limit. And we looked at a couple of problems today where we were able to simplify the given function by factoring and canceling common factors to get a function, a second function, that agrees with the original function at all values of x except x is equal to c, at which we were taking the limit. But again, that's okay because when we are taking the limit, we don't care what's going on when the input is equal to c. We care what's going on when the input values are close to c.